Hello, we're the Three Stooges. I am Josh. With me today is Cooper, and special thanks to Daniel for putting our video together for us. The problem that the team, the Three Stooges, set out to solve is that of pizza delivery via a drone. This problem has many issues that the team identified as areas where a control engineer could fix. First, the team identified that the drone may not be flying smoothly because of winds and unsteady stabilization. In feedback systems, this is called a disturbance. A feedback engineer can design a system in such a way to reject these disturbances. Another problem area that the team identified was that the drone may be dropping the pizza from too high above the ground, causing damage to the pie and the box. This would be classified as an error in the system. An engineer with the proper tools can minimize this error and can also make the drone land smoother. Finally, the evidence of pizzas on roofs was indicative of drones flying too close to houses. A control engineer could design the system in a way to increase the overall drone flight height. The problems are applicable to the real world, and the solutions are found in the tool belt of a feedback engineer. When looking at a system model, in the top right, we can see the open system that was provided to us in the problem statement. On the left is a physical system model providing a upwards force of 50 newtons on the rotors. We didn't end up using 50 newtons, but this was given to us in the problem. And then we have a force of gravity in the negative y direction, as well as a dampening force in the negative y direction, which is wind resistance in the case of a drone here. In the bottom right, you can see the system circuit for the drone, provided impedances. If we continue on, we can see how we got the transfer function for our system. It is important to note that we used a value of C of 1.1, which is the thrust to weight ratio of our drone here. In the upper right hand side, we can see a chart providing thrust to weight ratios that we got offline. We used 1.1 to allow for smooth flight because we didn't want too high of a thrust to weight ratio, which may make the drone fly too rapidly and unsteady, especially when handling a pizza. We used a mass of the drone of 2.25 kilograms, which we got online from a source that was selling drones, and then we have a dampening ratio of 3, and we have a gravitational force of 9.81 meters per second squared. In the bottom right hand, we can see a step response for the drone as it increases in height over time. A quick analysis of the open loop plant shows that the system is unstable. The first indication that this system is unstable is the fact that it is an open loop system. This states that the input to the system doesn't know the output. Therefore, the system will always be unstable. Another method of showing that this system is unstable is by looking at the system type. This system has one pole located at the origin and the other pole located on the negative real axis at 1.33. The one pole at the origin classifies the system as a type 1. By definition, an open loop type 1 system is unstable to a unit step response. Finally, based on the team's knowledge of Newtonian physics, it can be seen that the system will accelerate to infinity and therefore be unstable. Because the net force on the drone is upwards and constant, the drone will continually accelerate upwards. This acceleration will never stop and is therefore unstable on the system. Moving on to Cooper with the design specifications.